Alright, so we talked about finding limits analytically. Now let's talk about some more complicated functions. Remember that when we do the analytic approach, we're either going to use some algebra or calculus. One of our common techniques is to just try and see if we could substitute it in, or we could see if it's factorable, and then therefore reduce some of the factors out, or we can see if we can just multiply by a conjugate method. Now the conjugate method isn't as always easy to see as possible. Usually when you have a square root, especially in the denominator, that's probably going to be a conjugate method, but there's other ones where there's conjugate method involved. So let's take a look at some complicated ones. Alright, this first one involves a cubic expansion. And so to review that, I put some of the sum of cubes and the difference of cubes expansion formulas here. Kind of the way that I always remember this is the acronym SOAP. If you look, this sign is the same sign, so it's just the first term plus the second term, or if it's minus, and it's the first term minus second term. And then it goes the opposite sign, and then this last one is always positive. So then it would just be the first term squared minus first times the second, and then plus the last term squared. And that term is always positive, and then this is the opposite sign. So see how this is the same sign, opposite sign, always positive. So that's kind of how I remember that. So as we look at this first function, we want to factor this thing out. So this obviously is a sum of squares on top, or a sum of cubes, I mean. So I'm going to say the same sign. Oh, first maybe it'd be helpful if instead of an 8 you saw that as 2 cubed. That's what you really have to see that as. So this is like saying x plus 2 times x squared. Now we need the opposite sign, so this is going to be minus, and this is 2 times x. And then always positive, the last term is going to be 2 squared, which I'll eventually write as a 4. The thing that you need to see here is that this is really like saying x squared minus 4 squared. And then what you have is a difference of squares. And so a difference of squares can go as x squared plus 4 and x squared minus 4. The reason why that's important is now we have another difference of squares here that we could keep factoring. So I'm going to write that right to the right. So we really have, and this whole time actually I should have been including the limit notation, so let's put that back in. The limit as x approaches -2 is, we got x plus 2, x squared minus 2x plus 4. Okay. Let's make that into an actual x. And then on the bottom we had an x squared plus 4. That's not really factorable, so I'm just going to leave that as is. And then we could factor this as a difference of squares as well, because this is like saying x plus 2 times x minus 2. Now from the very beginning I should have shown you that if we wanted to substitute in at the very beginning it wouldn't have worked. Let me just rewrite what we had here. We had an x cubed plus 8 over x to the 4th minus 16. And if we would have taken a -2 and just plugged it in, right, for the x, direct substitution, we could have seen right away why this won't work, so I'll show you. So you would have had a -2 cubed plus 8 and a -2 to the 4th minus 16. Well, -2 cubed is positive, or sorry, it's -8. But -2 to the 4th is positive 16. And so you end up with a 0 over 0, which is undefined, and so we can't evaluate it using direct substitution. That's usually what we want to do first. I just already knew that you couldn't do that, so I skipped it. I apologize. So let's go on to where we have this thing all the way factored. You'll notice now that the x plus 2 and the x plus 2 can cancel out. And so now we have a lot simpler function. I'm going to write it down below. Now we really just have to evaluate the limit as x approaches -2 of x squared minus 2x plus 4 over x squared plus 4 times x minus 2. And now let's go ahead and use direct substitution. Now that we've canceled out a factor, we might be able to go ahead and use direct substitution. So if I plug in a -2, I would get -2 squared minus 2 times negative 2 plus 4, that's a 2, over negative 2 squared plus 4, negative 2 minus 2. Alright, see if we can clean this up a bit. Negative 2 squared, well that's just positive 4. Negative 2 times negative 2, that becomes also positive 4. And then we have a plus 4 at the end. Over negative 2 squared, that's also positive 4, so this is like a 4 plus 4. Times negative 2 minus 2, that's a negative 4. Alright, and finally 4 plus 4 plus 4, that is 12 over 8 times negative 4. So that's like 12 over negative 32. And this is definitely factorable. We could reduce each of these by 4, which gives me 3 over 8, and it's negative, so negative 3/8. So there we were able to evaluate that limit. I know it's a little nasty, but we were able to do it by factoring it, canceling out common factors, and then using direct substitution. Pretty common strategy with these limit problems. Let's go to the next one. Okay, so as with all of these, I kind of want you to just take a look at it, maybe pause the video and see if you can't think of a strategy that might work on how to attack this problem. So I'd go ahead and do that now. Just pause and take a look, see if you can do it yourself. If not, no worries, I'm about to do it for you. All right. Right away I see a 4 minus the square root. And I know right away I can't use direct substitution because if I plug in a 0, I'm going to be divided by 0. So can't do that. But I do see this term minus this other term. And so I think that maybe a conjugate rule might work really well here. So let's go ahead and do that. Let's multiply the top by 4 plus, parentheses here, 4 plus 16 minus x. That's its conjugate. But we're going to do the same thing on the top and the bottom. And remember, when we do this, we can leave the bottom, or the one that we're not multiplying the conjugate by, which is this one, just leave it in factored form, because we may see some things just kind of cancel out. So we're really asking the limit as x approaches 0 of. The conjugate rule is you square the first term, so that's just 16, minus the square of the second term. Well, since this is under the square root, that's just going to be 16 minus x. All over x, 4 plus square root 16 minus x. We could simplify this a little bit. If we were to distribute this negative sign, you'd end up with a negative 16 and a positive x. And obviously 16 minus 16 cancels out. So x over x times 4 plus the square root of 16 minus x. So I see here that I have an x on top and x on bottom, so that means that I can reduce that, and so I'm really asking the limit as x approaches 0 of 1 over 4 plus the square root of 16 minus x. Alright, we've got this thing simplified quite a bit. We might actually be able to do direct substitution now, so let's just see. 1 on top, 4 plus the square root, 16 minus 0. Yeah, this is going to work just fine now. So, and basically once you plug it in, once you do direct substitution, you don't need the limit notation anymore. Technically it should have been up here. And this is all just if you were doing a free response question, all this work should be in there. So I got 1 over 4 plus 16 minus 0 is just 16, and the square root of 16 is 4, so 4 plus 4. And that's 1 over 8. Boom, we got it. Here's another one. This one's interesting because we're not using numbers, we just have these variables, but no big deal. Let's go ahead and just, you can see right away, first of all, why you can't just use direct substitution. If you plug a b in for x, you just get b minus b, which is 0. So that's not going to work. But I definitely think we can factor this because it's a difference of squares. So let's go ahead and do that. It would equal the limit as x approaches b, x plus b, x minus b, over x minus b. These cancel, and so now we have a really simple problem. It's the limit as x approaches b of just x plus b. Well, there's no reason why we can't do direct substitution now. There's no 0 in the denominator here. So if I plug that in, I just get b plus b, which is equal to 2b. So whatever b is, the limit as x approaches this thing would just be 2 times b. Easy. Let's go to the last one here. Alright, these are really fun ones. First, what you got going on here is some fractions divided by another, like binomial here, which really means you kind of have like a fraction within a fraction. So I'd say let's just kind of clean this up by thinking of this as x minus 2 over 1. And so when we do that, we have the limit as x approaches 2 of, we have 1 over x minus 1/2. Let's put that in parentheses. And instead of saying divided by x minus 2, we could just flip and multiply, and that'd be like multiplying by 1 over x minus 2. Okay. Well, really what this is just a one term minus another term times this big fraction here. So we could just use the distributive property. So if you think about it, this is really the same thing as the limit as x approaches 2 of. Let's first just distribute this whole term to the 1x. Well, that would just look like this. Minus, now we can distribute this whole thing to the 1/2. That would look like this. Okay, well, we can kind of clean that up a little bit more. That's the limit as x approaches 2. So 1 times 1 is just 1. And then on the bottom, let's leave it in factored form because we're going to get common denominators in a second. So on the bottom, I would just have x times x minus 2 minus 1 over 2 times x minus 2. Now the next step is to get common denominators, but we're really close to common denominators. If you look at this, they both have an x minus 2. This one just needs a 2. This one just needs an x. Something you did back in Algebra 2, hopefully remember it. But all you have to do, if you think about it, is multiply the top and bottom of this by 2, and multiply the top and bottom of this by x. You can do that because that's just a 1 and that's just a 1. You're not changing its value. But now look, you have a 2x and an x minus 2, a 2x and an x minus 2. You have common denominators. So that's the limit as x approaches 2 of, let's write our common denominator as one denominator, 2x, x minus 2. And on the bottom, or on the top, I have 2 times 1, so that's just a 2, minus 1 times x is just x. Alright, so that was a lot of tricky algebra, and we have one more interesting step here before we can start to really evaluate the limit. By the way, we couldn't have used direct substitution. Hopefully you saw. If you just plug a 2 in for x, you get a 0 in the denominator. Not going to work. So here's the thing that is a little bit weird, and you'll use this strategy on a lot of these types of problems, is that technically these two things, they're not the same, but we can make them be the same by factoring out a negative. Think about it. If you factored out a negative 1 of 2, let's put a negative 1 out here, what would this become? This would become negative 2. If you factor out a negative 1 of negative x, it would become positive x. So you factor out a negative 1, and now look, technically you have a negative 2 plus x. Well, isn't it the same thing as x minus 2? It is. So just to show you, you could rewrite this as negative 1 times x minus 2 over, I should have put the limit in here, over 2x times x minus 2. That's just to show you that those things are really the same. So that x minus 2 now cancels out, even though there's still a negative 1 on top. And you're left with the limit as x approaches 2 of negative 1 over 2x. And now you absolutely can just do direct substitution. You get negative 1 over 2 times 2, which is negative 1. fun problem, right? A lot of cool, tricky little things to do there, but it's a little bit of a challenge, but it's fun. All right, that's it for this video. I'll see you guys on the next one.